Behold Pascal's triangle. Whereas the Fibonacci numbers are listed in one infinitely long row, the numbers in Pascal's triangle are listed in one infinitely long triangle. Now, this triangle has a lot in common with the Fibonacci numbers. The Fibonacci numbers start with 1 and 1. In Pascal's triangle, the first and last entry in each row is 1. The Fibonacci numbers continue with 1 plus 1 equals 2. And the first interior number in the triangle is 2, which comes from the sum of the two numbers above it, 1 and 1. In fact, the numbers in the interior of Pascal's triangle also behave like the Fibonacci numbers. As we know, each Fibonacci number bigger than 1 is the sum of the two numbers before it, right? Like 13 is 5 plus 8. Likewise, in Pascal's triangle, every number bigger than 1 is the sum of the two numbers above it. For example, here we see that 10 is equal to 4 plus 6. And here, 15 is equal to 10 plus 5. What would the next row look like? Well, let's see. It would begin and end with 1, and the numbers in between would be 1 plus 6 is 7, 6 plus 15 is 21, 15 plus 20 is 35, and so on. Like the Fibonacci numbers, the numbers in Pascal's triangle appear everywhere in mathematics. You may recall from your algebra class that x plus 1 squared is 1x squared plus 2x plus 1. And x plus 1 cubed is 1x cubed plus 3x squared plus 3x plus 1. You might even remember that x plus 1 to the fourth is 1x to the fourth plus 4x cubed plus 6x squared plus 4x plus 1. These are called binomial expansions. I'll throw in x plus 1 to the 0, which is 1, and x plus 1 to the first power, which is x plus 1, for good measure. Now, if we look at the numbers that appear in these binomial expansions, what do we see? We see the rows of Pascal's triangle, right? The top row is 1, the next row is 1, 1, the next row is 1, 2, 1, 1, 3, 3, 1, and so on. Because of this, the numbers inside of Pascal's triangle are called binomial coefficients. Originally, we presented Pascal's triangle as a centered isosceles triangle, but I think it's easier to appreciate its patterns as a right triangle, so let's write it that way. Some say the right triangle is the right way to write it. All right, so just like in the original form, each row begins and ends with 1. The other numbers are the sum of the number directly above it and above left. For instance, this 20 is equal to 10 plus 10. Notice that the left-hand column has all 1s in it. We call that column column 0, and we call the top row row 0. The next column has all the positive integers. We call that column column 1, and label the rows to match its integer. The numbers in column 2, 1, 3, 6, 10, 15, and so on, are called triangular numbers, since with those many dots, we can create nice right triangles. For example, the fourth triangular number, 1 plus 2 plus 3 plus 4, is 10. The fifth triangular number is 1 plus 2 plus 3 plus 4 plus 5, which is 15. Look at what happens when you add consecutive triangular numbers. 1 plus 3 is 4, 3 plus 6 is 9, 6 plus 10 is 16, 10 plus 15 is 25. Those numbers 4, 9, 16, and 25, they're perfect squares. 2 squared, 3 squared, 4 squared, 5 squared. This makes sense, since when you add two consecutive triangles, you get a perfect square, like so. Notice that when we add the fourth triangular number to the fifth triangular number, that is 10 and 15, we literally get 5 squared, which is 25. We give the number that appears in row N and column K a name. It's denoted like this, and it's pronounced n choose k because it counts the ways that we can choose k objects from n different objects. These are also called combinations. For example, the number that appears in row 5, column 2, the number 10, is equal to 5 choose 2. Why is that? Well, we're counting the number of ways to pick 2 objects from a set of 5 different objects where order does not matter. For example, all right, we'll illustrate 5 choose 2 here. From the set of numbers 1, 2, 3, 4, 5, there are 10 ways to choose 2 different numbers, right? 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, and 4, 5. Notice we don't include 2, 1 because order doesn't matter. See, 2, 1 is the same as 1, 2. We say that these numbers, these 10 numbers, are the size 2 subsets of 1, 2, 3, 4, 5, and they're counted by the number 5 choose 2. Similarly, 5 choose 1, which is 5, counts the ways to pick 1 object out of those 5. Obviously, there are 5 ways to do it. 5 choose 3 is 10, counts the size 3 subsets, and they are shown here. 5 choose 4 is 5, counts the size 4 subsets. And 5 choose 5 is 1, counts the one way to pick all 5 objects, namely 1, 2, 3, 4, 5. Also, 5 choose 0, that's also 1. That counts the ways to pick no objects. The number of ways to pick nothing, denoted by the empty set. Just like with Fibonacci numbers, the numbers in Pascal's triangle have all kinds of amazing patterns, and we can use their counting interpretation to explain them. For example, let's see what we get when we sum each of the rows of Pascal's triangle. Now, the top row adds up to 1. The next row, 1 plus 1, adds up to 2. The next row, 1 plus 2 plus 1 is 4. Then they add up to 8, 16, 32, 64. We're getting powers of 2. Specifically, it looks like row n will add up to 2 to the nth power. For example, row 5 sums to 32, which is 2 to the 5th power. One way to understand this is to notice that each number in a given row contributes twice to the row below it. For example, this number 4 contributes to 4 plus 1 equals 5, and 4 plus 6 equals 10. As a result, the sum of each row should double each time. Consequently, if the numbers start out like powers of 2, then as they double, they will continue to be powers of 2. Alternatively, we can take a counting approach. Here, let's look at row 5. As we saw earlier, the numbers in row 5 count all possible subsets of the set 1, 2, 3, 4, 5. A subset could be as small as the empty set with 0 elements, or it can have 1 element, or it can have 2 elements, and so on. In other words, there's one subset of size 0, and that's denoted by 5 choose 0. There are 5 choose 1, 5 subsets of size 1. There are 5 choose 2 subsets of size 2, 5 choose 3 subsets of size 3, 5 choose 4 subsets of size 4, and 5 choose 5, one subset of size 5. Altogether, the number of subsets is 5 choose 0 plus 5 choose 1, all the way up to 5 choose 5. But why should that equal 2 to the 5th power? Well, another way to answer that same question is to decide for each element whether to put the element in the subset or not. For instance, if we look at the elements 1, 2, 3, 4, 5 and decide yes, yes, no, no, yes, then that gives us the subset 1, 2, 5. And since we have 2 choices for the number 1, either we include it in the subset or don't, and 2 choices for the number 2, 2 choices for the number 3, and so on, then the number of possible subsets is 2 times 2 times 2 times 2 times 2, 2 to the 5th power. In general, if we're looking at the nth row of Pascal's triangle, we can do the same combinatorial proof. Our question is, how many subsets are there of the set 1 through n? Well, there are n choose 0 subsets of size 0, n choose 1 subsets of size 1, all the way up to n choose n subsets of size n. So there's n choose 0 plus n choose 1, all the way up to n choose n, which is the sum of the nth row of Pascal's triangle. Alternatively, we can decide for each element whether or not to include it in the subset, which can be done 2 to the n ways. I can't resist going off on a brief tangent. Here are all the subsets of 1 through 5, starting with the empty set on the top and the complete set 1, 2, 3, 4, 5 on the bottom. My question is, how many of these subsets have no consecutive numbers? I'll call these lonely subsets since no element has an immediate neighbor. Okay, so here are all the subsets of the set 1, 2, 3, 4, 5. And altogether, we can see that there are 13 lonely subsets listed here. If we look at smaller examples, what do we see? The set 1 has 2 lonely subsets, the empty set and the set 1. The set 1, 2 has 3 lonely subsets, namely the empty set, the set 1, and the set 2. The set 1, 2, 3 has 5 lonely subsets, namely the empty set, 1, 2, 3, and the subset 1, 3. The set 1, 2, 3, 4 has 8 lonely subsets listed here. And as we've seen, the set 1, 2, 3, 4, 5 has 13 lonely subsets listed here. 2, 3, 5, 8. Who do we appreciate? Fibonacci. So why should this be? Here, let's look at the lonely subsets of 1, 2, 3, 4, 5. There are 13 of them, right? Now, how many of them don't contain the number 5? Well, these are just the lonely subsets of the set 1, 2, 3, 4, and there are 8 of them. Okay, now how many do contain the number 5? Well, in order to be lonely, it can't contain the number 4 because 4 and 5 are neighbors, so it has to be attached to a lonely subset of 1, 2, 3, and we've seen that there are 5 of those. In other words, the lonely subsets of 1, 2, 3, 4, 5 consist of the lonely subsets of 1, 2, 3, 4, along with the lonely subsets of 1, 2, 3 with the number 5 attached to them. Hence, it must contain 8 plus 5, which is 13 lonely subsets. And this pattern of logic continues. Thus, since these numbers begin like the Fibonacci numbers and they grow like the Fibonacci numbers, then they must be the Fibonacci numbers. Okay, back to Pascal's triangle. We've seen that the rows add up to powers of 2. What can we say about the columns? All right, well, technically, each column has infinitely many numbers, so the sum would be infinity. But what if we add a bunch of numbers in the column, starting from the top, and then stop? Then what do we get? For instance, looking at column 2, if we add 1 plus 3 plus 6 plus 10, we get 20, which is in the next row of the triangle. Check it out. And that's not a coincidence. It happens everywhere in the triangle, right? 1 plus 4 plus 10, that's 15. This is called the hockey stick identity because of the shape that it makes. Here's a quick combinatorial explanation of what's going on. The number 20 appears in row 6, column 3. So that 20 is equal to 6 choose 3. The numbers being added in column 2, let's see, those are 2 choose 2, plus 3 choose 2, plus 4 choose 2, plus 5 choose 2. But why should that equal 6 choose 3? Now we know that 6 choose 3 counts the size 3 subsets of the set 1 through 6, and there are 20 of them shown here. Now I've written these 20 subsets in 4 rows, where these rows have 1 number, 3 numbers, 6 numbers, and 10 numbers respectively. The last row has all the subsets that contain a 6. Notice that these subsets are all of the size 2 subsets of 1, 2, 3, 4, 5 with a 6 tacked on to the end. Thus, there are 5 choose 2, that's 10 such entries. Similarly, the next row contains subsets that don't contain 6, but whose largest entry is 5. These are the size 2 subsets of 1, 2, 3, 4 with the number 5 tacked on to the end. Hence, there are 4 choose 2, which is 6 ways to do that. Likewise, the next row contains subsets whose largest entry is 4, and there are 3 choose 2, that is 3 ways to do that. And the first row has the subset whose largest entry is 3, and there's just 2 choose 2, 1 way to do that. As a result, 2 choose 2 plus 3 choose 2 plus 4 choose 2 plus 5 choose 2 must equal 6 choose 3. By essentially the same argument, we can prove the hockey stick identity for anywhere in the triangle. When we sum down column 2, we saw 2 choose 2 plus 3 choose 2 all the way up to 5 choose 2 is equal to 6 choose 3. When I sum down column K, we get K choose K plus 1 choose K all the way up to N choose K is equal to N plus 1 choose K plus 1. Okay, we've now summed the rows and the columns of Pascal's triangle. Let's finish up by adding the diagonals, starting in the leftmost column and going up by 45 degrees like so. Starting in row 6, we get 1 plus 5 plus 6 plus 1 is 13. Checking the earlier diagonals, we get totals of 1, 1, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 plus 1 is 5, 1 plus 4 plus 3 is 8, followed by 1, 5, 6, 1, which adds to 13. It's Fibonacci time! Where are they coming from? Let's see if we can explain why 1 plus 5 plus 6 plus 1 is 13. In other words, in terms of the binomial coefficients, this is saying 6 choose 0. Plus 5 choose 1, plus 4 choose 2, plus 3 choose 3 is little f6. Why should that be? Remember, little f6 counts the ways to tile a strip of length 6 using squares and dominoes. Let's break these tilings into 4 cases based on how many dominoes they have. Since the tiling has length 6, we can either have no dominoes, 1 domino, 2 dominoes, or at most 3 dominoes. So we'll look at each case separately. If there are 0 dominoes, then there's just one way to tile the strip using 6 squares, right? I'll denote that by SSS, SSS. Note that 6 choose 0 is 1, which is the first term in our sum. For the next case, suppose there's exactly 1 domino. Now with 1 domino and a tiling of length 6, let's see, we're going to need to have 4 squares to go along with that domino. That means we're going to have 5 tiles, right? 1 domino and 4 squares. So we take our 5 tiles and choose one of them to be a domino. Thus we have 5 tilings shown here. Again, note that the domino can either be the first tile, or the second tile, or the third, or fourth, or fifth. Thus, there are 5 choose 1, 5 tilings of length 6 that contain exactly 1 domino. All right, what if there are 2 dominoes? Then we have to have 2 squares, right? 2 squares and 2 dominoes. They have length 6. That means there are 4 tiles being used. Notice that there are 6 such tilings, as shown here. Notice that our 2 dominoes can either be the first and second tile, or the first and third tile, and so on. We simply choose 2 of the 4 tiles to be dominoes, and that can be done in 4 choose 2, 6 ways. Finally, if a tiling of length 6 has 3 dominoes, then there are no squares, right? There's just 1 tiling, namely domino, domino, domino. And notice that 3 choose 3 is 1. Thus, we've shown that the number of length 6 tilings with 0, 1, 2, and 3 dominoes is respectively 6 choose 0, 5 choose 1, 4 choose 2, and 3 choose 3. The same argument can be used that when we sum the nth diagonal, we must get the Fibonacci number little fn. That is, when we added the 6th diagonal, we saw that 6 choose 0 plus 5 choose 1 all the way up to 3 choose 3 is f sub 6. And when we add the nth diagonal, starting with n choose 0, then n minus 1 choose 1, then n minus 2 choose 2, and go all the way until we fall off the triangle, we get f sub n. This pattern shows us that the Fibonacci numbers are a fundamental part of Pascal's triangle, which I think is pretty amazing. Conversely, we can also show that Pascal's triangle can be discovered inside of the Fibonacci numbers. Here, let me show you what I mean. We know that each Fibonacci number is the sum of the previous two. For instance, our leapfrog rule says that f10 is equal to f9 plus f8. Now, if we replace f9 with f8 plus f7, and we replace f8 with f7 plus f6, this becomes f10 is equal to f8 plus f7 plus f7 plus f6. That's f8 plus 2 f7s plus f6. Okay? Notice the coefficients here are 1, 2, and 1. If we apply the leapfrog rule to each of these terms, for instance, if I replace f8 with f7 plus f6, and f7 with f6 plus f5, and so on, we now get f7 plus f6 plus 2 times f6 plus f5 plus f5 plus f4. And that's equal to 1 f7 plus 3 f6 plus 3 f5 plus 1 f4. And those coefficients are 1, 3, 3, 1. You see the pattern, right? The coefficients are 1, 1, then we had 1, 2, 1, and then we have 1, 3, 3, 1, and these are rows 1, 2, and 3 of Pascal's triangle. The next row is 1, 4, 6, 4, 1. And indeed, when we apply the leapfrog rule to each term in our equation, we have that f10 is 1 f6 plus 4 f5 plus 6 f4 plus 4 f3 plus 1 f2. And more generally, for n greater than or equal to 8, we have fn is equal to 1 fn minus 4 plus 4 fn minus 5 plus 6 fn minus 6 plus 4 fn minus 7 plus 1 fn minus 8. Let's explain this equation with a combinatorial proof by seeing what both sides of this equation are counting. We know that the fn term counts tilings of length n with squares and dominoes. And since n is greater than or equal to 8, there must be at least 4 tiles. If we look at the last 4 tiles in the tiling, the number of dominoes could be as little as 0 or as many as 4. If there are 0 dominoes, then the tiling ends with 4 squares, SSSS, preceded by a tiling of length n minus 4, and that can be done in fn minus 4 ways, as shown here. And that explains the first term of our sum. If the tiling has 1 domino among the last 4 tiles, then there are 4 ways to do that, depending on whether the domino is the first, second, third, or fourth tile, looking something like this. Here, the domino is our second tile among the 4 last tiles. By the way, no matter how those 4 last tiles are arranged, they're going to have length 5. And everything before those tiles, that's going to have length n minus 5, and that can be tiled in fn minus 5 ways. Likewise, if our last 4 tiles have 2 dominoes, they can be arranged in 4 choose 2, which is 6 ways, and the preceding cells of length n minus 6 can be tiled in fn minus 6 ways. Similarly, with 3 dominoes, they can be arranged in 4 ways, preceded by a tiling of length n minus 7. And finally, if the last 4 tiles consist of 4 dominoes, and there's just one way to do it, then the preceding cells of length n minus 8 can be tiled in fn minus 8 ways. and this explains our formula. To summarize, we showed earlier that the Fibonacci numbers appear in Pascal's triangle in an interesting way. And our latest result shows that the Pascal triangle is firmly embedded within the Fibonacci numbers as well. And I think that's pretty cool. By the way, I should mention that there is an actual formula for n choose k that we haven't needed yet, but it's worth knowing. It says that n choose k is equal to n factorial divided by the product k factorial times n minus k factorial, where n factorial is the product of all the numbers from 1 to n. For instance, 3 factorial, that's 1 times 2 times 3, is 6. And 6 factorial is the product of the numbers 1 through 6, which is 720. That means 6 choose 3, which is 6 factorial over 3 factorial, 6 minus 3 factorial. That's 720 over 6 times 6. That's 720 over 36 is 20. As it turns out, the Fibonacci numbers have an even simpler formula, but we won't see that until we explore the golden ratio in a few more lectures. I can't resist showing you one more fun way where Fibonacci and Pascal dance together. Let's take any row of Pascal's triangle, say row 5, 1, 5, 10, 10, 5, 1. Below these numbers, let's write the first 6 Fibonacci numbers, 1, 1, 2, 3, 5, 8. Next, let's multiply the corresponding numbers together, then add them up. All right, so 1 times 1 is 1, 5 times 1 is 5, 10 times 2 is 20, 10 times 3 is 30, 5 times 5 is 25, and 1 times 8 is 8. And when I add up those 6 numbers, we get 89. Lo and behold, you get a Fibonacci number. In fact, it works with any consecutive Fibonacci numbers. Yeah, for example, let's say we took the row 1, 4, 6, 4, 1, and we took consecutive Fibonacci numbers beginning with the number 3. So 3, 5, 8, 13, 21. When we do our multiplications, 1 times 3, 4 times 5, 6 times 8, 4 times 13, and 1 times 21, and add up those numbers, we get 144, the 12th Fibonacci number. You always end up with a Fibonacci number. Like I've said before, the Fibonacci numbers are everywhere. There's a nice combinatorial proof of this fact, but I'll leave that as an exercise. Can it get any cooler than this? Absolutely. In fact, in our next lecture, I will share with you my favorite Fibonacci fact, and it's based on one of the world's oldest mathematical algorithms. I'll see you then.